Hello and welcome to The Zero Page, a companion series to my Thinking in 6502 videos. You can think of this as a bit like a DVD extra if you're old enough to remember those. If you've not already seen the Hello World video, I do recommend you go and watch that first, as otherwise a lot of this video isn't going to make a huge amount of sense. Now, as I said in my first episode of Thinking in 6502, it was aimed very much at those beginning their 6502 journey, and so in those videos I'm going to try not to assume any pre-existing knowledge outside of things like BBC Basic and general programming concepts. I personally think that's the right approach, but it doesn't always leave space to dig into some of the nuances and details of 6502 programming. In assembly world, things can get pretty heavy pretty fast, and the last thing I want is to lose anyone who's taken an initial interest, but then feels like they've been thrown in the deep end. So to get around this, I'll be making these companion videos as a place to explore some of the concepts a bit further, and it's entirely up to you if you want to watch or just wait for the next main video in the Thinking in 6502 series. If that hasn't already put you off, let's begin. First, I want to take a closer look at the machine code generated by our initial Hello World program attempt. Now, you can see that LDA has been translated here by the assembler to a hex byte of A9 in the machine code. Later on, however, when we passed the label text to LDA, that A9 byte disappeared, and it was replaced instead by a value of AD. Indeed, it changed again when we constructed our loop and used the X index register to work through each character, this time to a value of BD. But in all three cases, we're still using LDA, so what's going on here? Well, technically speaking, the mnemonic LDA is not an instruction on its own. It only becomes one in combination with the value that comes immediately after it in the assembly code program. Now, in our early program, we were using a value of #65. As I said at the time, the hash prefix is used to indicate that we're passing in an immediate value, which is to say the decimal value of 65, which becomes 41 in hexadecimal. I should probably say 41 rather than 41, of course. So the hex byte A9 is not the machine code translation of LDA, but rather the machine code translation of LDA followed by an immediate value. So what about AD and BD? Well, if you look at what follows the AD value, you get a bit of a clue. It's 2 bytes rather than 1, and if you read them backwards in the little endian fashion, where the low byte comes first, they correspond with the memory address storing the first character of our string, 0E95. And thus the hex byte AD is the machine code equivalent of LDA followed by a memory address. To be even more precise, we should say a direct or absolute memory address, insofar as the 6502 will go to the memory address OE95 and place whatever byte it finds there into the accumulator. Later on, after we constructed our loop using the X index register, the hex byte changes to BD, which is another variation of LDA, and we're still giving an absolute memory address, but we're also asking the 6502 to offset that address by the value of the X index register. A9, AD and BD are not the only variations of the load accumulator instruction either. There are several more besides, each with their own specific command to the 6502 about precisely how and what it should load into the accumulator. We'll likely meet more of them as the series progresses, but for now just be aware that a single mnemonic in 6502 assembly code doesn't always correspond to the same hexadecimal byte in machine code in every scenario. So the next thing we're going to have a look at is, in our Hello World program, we used the JSR instruction, and I said at the time that this is the basic equivalent of GoSub. JSR expects to find an executable subroutine at the address we give to it, just as GoSub expects to find basic commands that it can run at the line number that we pass to it. Both JSR and GoSub are only responsible for taking the program to that executable code, and they must be paired with another command if we want the program to continue executing from the point where they were originally called from. Now, with GoSub we have the return command. If we look at this simple BBC Basic program here, you can see that when we call the go_sub command and it goes to the line to call the print command, it's immediately followed by a return, and that takes us back to the program code so that it can execute the print command that comes after the call to go_sub. Of course, if we remove the return in line 60, the basic interpreter will keep running what it finds at the line number that you provided to go_sub and any lines forward from there until or unless it finds a return. But without a return, it just keeps running until the end of the program without returning to the point from which it was called, and as a result it might well end up executing code that we didn't actually want it to. Well, JSR works in exactly the same way. It's just that instead of return we have RTS, a mnemonic that means return from subroutine. Well, hang on though. In our Hello World program, where was the RTS that allowed the code to continue running after calling the Osrich routine? Well, we don't see that in our code because all our program does is use JSR to make a call to Osrich. None of the code of Osrich itself is inside our program. But if you were to go looking at the code for Osrich, which naturally is written in pre-assembled 6502 machine code, you would find that the final byte of the Osrich subroutine is itself an RTS command. And we can even verify this by checking the source code of Osrich itself. And don't you just love that about 8-bit home micros? The code for everything that they do is in ROM or RAM, and you can just go and have a poke around and see how it all works. And we're going to do that. Now, without getting too far into the weeds, the memory address FFEE does nothing more than tell the 6502 to go look at another memory address, in this case 020E, with the assurance that that memory address itself will contain yet another memory address for the subroutine code. This is called indirect addressing, and we're not going to get into it right now, but suffice it to say, address 020E holds another address, E0A4 on the BBC Micro or DE2D on the Acorn Electron, and that's the one which actually stores the starting byte of the code for the Osrich routine. Now, in BBC Basic, you can peek at the contents of a given memory address using the question mark, also known as the indirection operator. Prefixing this with a tilde symbol will output the result in hexadecimal. So I can write a simple basic loop to check the source code of Osrich by starting at address DE2D on my Electron and working forwards. I happen to know that Osrich ends at address DEA3 on the Electron. That's E113 on the BBC Micro. So if I step through each byte between DE2D and DEA3, I can see each byte of Osrich. And when I arrive at address DEA3, I find a byte value of 60, or 60, which is the hexadecimal machine code byte for RTS. All of which is to say, when you call Osrich, Osrich itself contains the RTS command that ensures that your calling program can continue running directly after that call has completed. If it didn't, the 6502 would just move on to the next byte and attempt to execute that command. Just like writing a basic program with a go_sub that doesn't have a matching return. An alternative instruction, which our Hello World program didn't use, well at least not directly, is the JMP or jump command. This command really is like goto in BASIC, and it can be used to redirect to a label or a memory address. I mean, strictly speaking, labels are really nothing more than memory addresses, it's just that we've chosen to give them a name within our program code, and that makes them easier to refer to. JMP exhibits the same behaviour as goto, albeit that goto does it with a line number. The difference with JMP compared with JSR is that JMP moves the program counter to that label or memory address, and the code simply executes from that point forward. There's no going back, because JMP doesn't take note of the current program counter value. JSR, by contrast, does do so, and in fact it is this note of the program counter's value that RTS subsequently uses to return execution back to the point from which JSR was originally called. Now if you're really clever, you can write this note yourself and then use RTS on its own to jump to it without even needing a previous JSR. This note of the program counter's value is put onto something called the stack, and that's a concept that we'll return to in more detail in a future video. Incidentally, I did say that our Hello World program didn't use JMP directly, but in fact there is a JMP command there. It's what we find at the FFEE address, and it is that jump which is responsible for telling the 6502 to go to address 020E, which is the one that contains the address of the first byte of the Osrich subroutine. Now, both JMP and JSR use 3 bytes of machine code, 1 byte for the instruction itself, and 2 further bytes for the memory address. For JSR, that's going to be a memory address of a specific subroutine from which we will want to return once completed, while for JMP it will simply be a memory address that contains the code that we want the 6502 to run from that point onwards. One final nugget of wisdom on this point. You can actually save a byte as well as a few CPU cycles if your own assembly code happens to finish on a call to a subroutine that you know contains its own RTS. Rather than using JSR, you can instead use JMP, knowing that the address that you're jumping to contains a subroutine that itself ends with an RTS. That RTS will as a result be the final byte of machine code executed by your program, and that allows a neat handoff back to BASIC again without the cost of an additional RTS at the end of your own assembly code. Of course, this only works if a subroutine call happens to be the final step of your own assembly program, and it does arguably make the code slightly harder to read, but hey, a byte saved is a byte saved. Now, our Hello World program doesn't use JMP to go back to the start print label. Instead, it uses the BNE or branch not equal instruction. And this is a branch, it's not a jump. BNE translates to a hex byte of D0 in the assembled machine code, but notice how there is only 1 byte immediately following D0, a value of F5. This doesn't appear to correspond in any way with the memory address of our start print label. That's because BNE uses relative addressing, meaning that F5 is being used to tell the 6502 where, in relation to the BNE command, it should branch to. F5 is therefore a simple number. It just tells the 6502 go back or forward this many instructions and execute from that point. But what number does F5 equate to? Okay, now I did say in my Hello World video that I was not going to get deep into number theory, but well, you might have noticed one of the text pop-ups in that video said that a single 8-bit byte is capable of storing integers from 0 to 255 or signed integers from -128 to 127. With unsigned integers, all 8 bits of the byte are used to represent the number, whereas with signed integers, the highest bit is reserved as an indicator to say whether or not the number is positive, in which case it'll be a 0, or negative, in which case it'll be a 1. BNE uses signed integers, and thus F5 is equivalent to -11 in decimal, and it quite literally means go backwards 11 bytes, which takes us to the start print label. Now, branching is great if your labels are plus or minus 127 bytes away from the point that you wish to branch from or to, because it only uses 2 bytes rather than 3 in the case of a JMP. In the memory-constrained environment within which assembly programmers operate, that really is a considerable saving. However, it does come with the limitation that if you need to go to an area of program code that happens to be more than 127 bytes away, forwards or backwards, well, you can't use a branch, you have to rely on a jump, and incur the additional byte cost. The good thing to know is that if you do try to branch to a label more than 127 bytes away, well, the assembler's going to tell you and it'll throw an error, so you don't have to calculate it yourself. Having said that, it's probably still a good idea to have a rough grasp of how far away you're intending to branch to from a program design perspective. I mean, don't forget, back in the day, some of the greatest assembly code programmers wrote most of their code using pen and paper long before they started entering it into the computer just to be able to plan everything out. Now, if you're doing it that way, you really do need to make these calculations up front. Hello World basic program, I used the len function as the basis for my for loop's exit condition. Now, I said at the time, well, we can't use len in 6502 world, and so based the CMP operation on the control character at the end of the string. While that did work, it would pose problems for us if we wanted to print strings that contained legitimate control characters in order to print at a particular location on the screen, just as we might do with a print tab in BASIC. As it turns out, we actually can simulate the len idea in 6502, it just requires a bit more thought than I had applied in my original program. So, just as A, X and Y each have their own load commands, LDA, LDX and LDY, they also have their own compare commands. Now, I used CMP in the original Hello World program, which is used with the accumulator, but X has its own CPX compare command, just as Y has its own CPY compare command. Where CMP compares the value currently loaded into the accumulator, CPX and CPY compare whatever value X and Y are currently set to. This means if we know the length of our string, we can compare X to that length, and when it's not equal, branch back to the start of the loop. X, as you recall, gets incremented each time we move through the loop. So when it reaches a value of 15, which would be the full length of our string inclusive of its new line control characters, this would mean that we've finished printing each byte of our string. But hard coding a value of 15 as our exit criterion is surely worse than checking for a control character. Well, this is where things get really clever, because not only can we dynamically calculate the length of our string inside our assembly program, we can also get the assembler to pre-calculate it, meaning that we don't need to spend any bytes on that calculation in our program code. So we can both dynamically calculate the value and hard code it at the same time. Now, how is that magic going to be performed? Well, it's all done with labels, believe it or not. As I said before, labels, well, they're really nothing more than memory addresses, and memory addresses are nothing more than numbers. So that means that we can perform arithmetic on them. If we subtract the value of our text label from the value of our start label, we get the total number of bytes that our string is occupying in memory. That subtraction operation can be done as a part of the assembly code itself, so that when the code is assembled into machine code by the assembler, the value of 15, which is to say 0f in hex, is preset for us by the assembler. Tricks like this are incredibly valuable when it comes to saving bytes, something that you really need to care about when working with a machine that only has 32K of memory to begin with. Well, that's all we've got time for this episode of the Zero Page. In the next video of the Thinking in 6502 series, I'll be going back to BBC Basic and trying my hand at something new, before then seeing how the equivalent can be done in 6502 assembly. I hope that you've enjoyed this companion video. Please let me know in the comments if you think it's a good idea to have these separate videos alongside the main ones. As I said at the start, I think it's helpful to kind of separate the deep dives from the main series, just so that it doesn't put too many people off if you're still new to 6502. But equally, if you think some of this material could have been put into a main episode, happy to hear that as well. In closing, just one more final point. I did get rather a lot of comments for the first video in Thinking in 6502 about the audio levels. I've done my best to try and correct that for this video. I hope it's made a difference. I hope you found it easier to follow along. Again, please let me know if not. Which just leaves me to say, I hope you'll join me for the next video in the Thinking in 6502 series, the main series, which is what I'll be working on next. I was honestly blown away by the response and the reaction to that first video in the series, the Hello World video. I'm very, very grateful for all of you who have given me feedback and who watched the video, and for all of those of you who chose to subscribe off the back of it. I hope that you'll continue to join me along this journey of 6502 assembly programming, and until the next time, goodbye.